LIGO stands for the Laser Interferometer Gravitational Wave Observatory.
LIGO is really two observatories that work in unison and tandem. The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. It produces light that's so coherent that it's capable of detecting gravitational waves.
We have these very massive mirrors. They weigh 40 kilograms, which is about 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was going to be a very high-risk experiment. It was from its very inception.
If you think about this in the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of LIGO. What the gravitational wave does is it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you made this long enough, if you didn't make it a little pipsqueak thing like this, but you made it sort of kilometer scale, you could probably get these extremely precise measurements.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
The precision that was required was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.